this computer. Okay. All right, so I like to put an outline up just so you kind of know where we're going. I thought about putting it on the board, but then guests can't see it. I'm gonna put it here. It's not something you really have to write down. It's just kind of like, this is what we're gonna do today, okay? But this way everybody could see it. I may do it in Calc if I remember. Okay, so I wanna start by talking about distance versus displacement, okay? Because that was one of the big ideas that you read about for today, okay? So what does distance mean? What does distance measure? Lauren. Okay, so it's the magnitude. Well, it's not just a magnitude with no direction. It measures something really specific. What units are we going to use for distance? We're going to use meters, and that's a unit for what? Length, okay? So distance is going to be the length what? The object travels. It's going to be the distance you actually move. I like to think of it sometimes as the number of steps that you actually take. Okay, so if I needed to go from here to, and guess in case you didn't know, we are in Miss Pasiak's room. If I needed to go from Miss Pasiak's room to Miss Heaps's room, which is right next door, I would have to go down the corridor by the chem room, go downstairs, go outside through the courtyard, go around to the front of the building, come down the skinny staircase where all the English teachers are, go by the bathrooms, go by the senior lounge, come up the stairs, and there would be Mrs. Heaps's room, right? Okay, my distance would be every one of those steps that I took. But what would my displacement be? Annabelle? Where do I measure my displacement from? Dagny? From start point to end point. So my displacement would be an arrow that would go from here in Miss Pasiak's room, that way over into Miss Heaps's room, okay? So displacement is, I like to think of it as the number of actual steps, okay? I'm sorry, the distance. And the displacement is basically a line between where you start and where you end. Okay, and somebody brought it up earlier, and they are correct that distance is a scalar, and that makes displacement a what? A vector, okay? So we're gonna remember, as Lauren told us, that scalars are just an amount, okay? I could make that same number of steps and walk someplace else, okay? But displacement is not only that distance that is between my start and my end point, it's also a direction. So my displacement would be different if I went from Miss Heaps's room to here. The length of that vector would be the same, but it would point in the opposite direction, okay? Before we get into motion in 2 and 3 dimensions, we will backtrack and talk a little bit more formally about vectors, which is kind of the rest of chapter 2, but we don't need it to do what I want to talk about right now, okay? So we can travel many different combinations of distances. We can take many different paths, but have the same displacement. All right. Okay, so what I would like you to do, since we have time, is to do the distance versus displacement activity. Okay. And that is going to involve using PhET. Okay, for vector addition. And I don't know how I told you to do it. Lab, I guess. Oops, wait, it went to my edge. So you want to press this one here, okay, for lab, and go from there. All right, so we'll take a little time. Guess you should be doing that as well. And perhaps I will pause the recording for a little bit so that we don't have like 15 or 20 or 30 minutes of you guys just working, okay? Questions? Okay, then I'm gonna. So you should start to take a look at your classmates' answers and see what you notice. Why don't you write next to your picture what your distance and your displacement were, just so that everybody can see, because one of the questions is how do they compare? All right, so Lauren's done, Fiona's done. Who's this? Oh, okay, that's okay, because like it didn't pop up with your initials, so that's Dagny. That's Gas. I thought it was Gas. Gas is down here. Who's this? Okay, that's Sophie. Good. That's Gas. That's Tia. So, Annabelle, you still coming? That's cool. No, that's all right. Just trying to get a feel for where we are. good? Okay. Let's just.
I keep writing and then it just like duplicates on top of itself like that.
That's okay. You can give us your answer, Dagny, when we get there. All right. I'm not. Okay. So while Annabelle works on that, what do you notice here about all of these graphs as we look at them? You must notice something. Okay, so Fiona says that the displacement is the same, but the distance is different. So remember, the distance is the path that you're actually moving. So you can see how these are all different paths. I worked very hard to make them all different paths. Okay, but remember, what is displacement? So Dagny says displacement is that line that joins the start to the end. Okay, so where did everybody start? We all started at the origin, and then where did everybody end up? Plus 26 in the positive x direction, right? Okay, so remember, displacement is a vector, so it's not just that it's 26, it's that it's 26 in the positive x direction. So we all ended up in the same place, right? Okay, I didn't mess that up. I don't think I did. But we took different paths to get there. So let's see, were there any other questions here that we have not answered? So number 11 here, what do you think is gonna happen if you click your origin and move it someplace else? I don't want you to redo your measurements, but what happens if you just move your origin? What's gonna happen, Lauren? Okay, so Lauren says that your displacement shouldn't change, that those vector, and I'm going to elaborate on that and say that those vectors exist independently of where the origin is. A vector is made up of a length and a direction, as we'll talk about in chapter, I don't know, 2, whatever it is, new textbook. So I can move those vectors anywhere. It doesn't matter where the origin is, and those vectors are going to have the same properties. So when I add up all those vectors, it's still going to be the same length between the beginning point and the end point, no matter where I have that origin, as long as I am measuring all of the vectors with respect to the same origin. Okay, Dagny, go ahead. Dagny wants to know if you have to do a squared plus b squared equals c squared to find the displacement, only if it's a triangle. And it doesn't matter. If I walk from here to here, okay, so I walked between 2 squares, I can take that vector and I can put it in any room in the building, and as long as it's pointing whatever angle northeast that is, that vector is the same, no matter where I put it in the building. It'll get a little wacky if I move it like between floors, but we're only dealing with 2 dimensions right now. Okay. All right, so questions on this. Okay, so a little practice in how we add vectors, a little demonstration that you can all have the same displacement even if you all have different paths. Okay. All right, so this was kind of like a physical, real world representation of what was going on. But now I'd like to look at it from a graphical, and I don't mean graphing the vectors, I mean looking at the graph of the motion. So the next thing I want to do is ranking exercise number 8, which looks like this. Okay, so please read the directions. And then what you're supposed to do is rank which you think is whatever. They tell you what they want you to rank it as. And we'll just take a minute or two to do that. Guess, can you talk to me for a minute? Just say hello or something.
Hello.
Okay, I totally screwed it up. I can't hear you at all. Never mind.
Hello.
I'll change that. All right, Guess, talk to me again, please.
Hello.
Okay, I can hear you now. You can't hear her though, can you? Okay, all right, that's okay. I thought maybe we could try something and see. What if? Audio settings. Nope. You weren't here before when we did that for like 10 minutes, and I tried to figure out how to make it work. I was hoping we could hear Guess's voice, but I can't seem to make that happen. Okay, are we done? All right, so I'm gonna ask some questions here. First of all, what are we graphing? Guess, what are we graphing in these graphs? What's on the vertical axis? What's on the horizontal axis?
The X is distance and T is time.
Okay, so Guess says that X is distance and T is time. Okay, so what's going on in each of these graphs? Okay, so Tia, what's going on in graph A? Okay, but what does it mean? Describe the motion that's going on in A. Okay, so Tia says we're not moving in A, right? Because no matter what happens with time, my position is still X equals 30, wherever X equals 30 is. Okay? So, Sophie, what's happening in B? Okay, so Sophie says that in case B, we're not moving either, we're just at a different position and not moving. Okay? Eva, what's happening in C? Okay, so Eva says in C, we're moving at a constant rate. Annabelle, what's happening in D? Okay, so in D, we are also moving at a constant rate. Which direction are we moving in C and D? The positive direction, okay. Lauren, what's happening in E? Okay, so Lauren says in E, we're moving towards the origin, but in a negative direction. Fiona, what's happening in F? Okay, so it looks toward and back what? So where are we starting in F? We're going to start at the origin. Okay, we're going to start at the origin, move to 8, x equals 8, and then move back to where we started in the origin. Okay, good. All right, so everybody understand what's happening in each of these graphs now. Okay, so Dagny, it doesn't matter how you did it, okay, because we're all friends here. So Dagny, tell me, what's your ranking here? And I've lost my purple writing thing. Just give me the letters. What is it? C, D.
And then I had A, B, and F off there because they're not, like, there really isn't a change in displacement.
Okay, so they're all equal, and that was the whole thing, is if they were equal, and then E. Okay, so is she right? We're all complimenting Dagny because it was beautiful. Guess, is this what you got? Yes, excellent. Okay, so congrats, you did it. Okay, all right, so okay, that was good. So now we're gonna go back, we're gonna do a few more notes. All right, so the book also talked about average velocity. Okay, and I like to abbreviate that VAV. Oh, that so does not work. Oh, there we go. And now my glasses are fogging up. All right, so what is average velocity? What's the definition? Dagny. It's not the average speed over a certain amount of time. Because that would actually give you really weird units, right? Okay, Annabelle, you want to try? It is, in fact, your displacement over whatever your change in time is, okay? So I might write this again as displacement over delta t, okay? So if average velocity is going to be the displacement over the amount of time it takes us to do that displacement, let's look back at these graphs for a minute. Okay, so what was our average velocity in part A? I'm sorry, in graph A? 0, right? Because we weren't moving anywhere. What was our average velocity in B? 0. Okay, again, because we're not going anywhere. So that's an observation. And I know Ms. Winkowski just did this whole thing on observations and inferences. So let's make an inference. What else about graphs A and B is equal to 0? The slope. Okay, let's look at C. What is your average velocity in graph C? Fiona says it's 1. How did you get 1?
Your displacement is constant, and the time is.
Okay, so Fiona says the displacement was positive 10, the time was positive 10, doesn't really matter. 10 over 10 gives me 1 for my average velocity. What else do you know about that line in C? The slope is equal to 1, right? It goes from 0, 0 to 10, 10. Okay, how about D? What's my average velocity in D? Annabelle? Is it really 5 over 10? What's my displacement in D? So displacement, remember, is where I end minus where I start. Nope. Where do I end, Annabelle? At 5. And where do I start? At 2. So what's my displacement? 3. Okay. And that's over 10 seconds. So what's my average velocity for D? 0.3. Okay. And what might the slope of that line be? How would you calculate the slope of that line? How do we calculate the slope of a line? Change in y over change in x. Okay. Vertical change over horizontal change, because we're going to get too many x's and it's going to get all wacky. Okay, but that's exactly what you just said, Annabelle, right? It was the change in the vertical direction over the change in the horizontal direction, 3 over 10. So are we getting a pattern here? What is my pattern? Okay, so the average velocity is also going to be the slope. And we can't just say the slope, okay? It's going to be the slope of what? A displacement versus time graph. Okay. So one more little thing to go back here, is velocity a vector or a scalar? It's going to be a vector, okay? Which means that it's not just a magnitude, it has a direction as well. So if we look at E here for a minute, which way are we going in E? How are we moving in graph E up there? In the negative direction, right? Because I'm starting away from the origin in the positive direction, and then I'm walking towards the origin. What can you tell me about the slope of the line in E? It's negative, okay? So that matters, and it's consistent. Okay, so what I'd like you to do is practice that yourself in ranking exercise number 10. Okay, which asks you to calculate the average speed of a bunch of graphs that look suspiciously like the ones in graphing exercise 8. All right. Who would like to share their answer? Tia, what'd you get?
I got E, and then C, D, and then A, B, and F all the same one.
See. Oh, that's right. It does say speed. Darn it. Okay, CD, and then what do you think?
C and D are in the same one, like C,
Okay.
and D, and then A, B, and F all in the same one.
CD. We got a whole flex time today. All right, so I should really change that to be average velocity because I'd much rather it be average velocity. All right, is she right? Okay, all right. So, move my notes over. All right, so we've decided that a changing position, okay, or distance or displacement, that a displacement versus time graph gives me a slope that's the average velocity, okay? And we'll talk a little bit more, you'll read a little bit more about how average velocity, how we turn that into instantaneous velocity if you haven't already. So, what happens now if my velocity is changing? What do I have in addition if my velocity is changing? Annabelle? I have an acceleration, okay? So if the slope of a distance versus time graph is average velocity, where do you think I'm going to find acceleration? You got a guess? Let's leave it there for the moment, okay? And we'll come back. So we're going to try to do a demo here. So I'm going to stop sharing my screen so that hopefully Guess is going to be able to see the demo. I hope I'm not making you motion sick, Guess. Yeah, but right now, actually, it's looking at me. So actually, I think what I want to do go is I want to put that over there. Okay, and Guess I'll turn it to the screen in a minute. Or actually, okay, and then we'll turn it back and forth. All right. Guess, do you see the stack of books? Okay, all right, so what I have is I have a ramp, okay? And I have a motion sensor that's at the bottom of the ramp. We'll get to that in a minute. And I have a cart. So what's gonna happen if I put my cart up here and I let it go? It's gonna what? I can't hear anybody. It's gonna accelerate. How do you know it's gonna accelerate? So the velocity is gonna change. What's the velocity gonna start at? 0, and what's it gonna end at? Something that's not 0, right? Because it's gonna move, okay? So I'm gonna let it go, but I have to catch it, okay? So the motion sensor actually lets us measure what those things are, okay? So we're gonna try this. I hope I'm not gonna be breaking any rules, but I can't work both the data collection thing and the card at the same time. So I think it's easier to wash this, okay? And actually, you're gonna have to wash, well, we'll just go with that, Okay, so I'm gonna need a volunteer to hit the button. Okay, Lauren, you wanna do it? Okay, so then what we're gonna do is we're gonna project the results on the screen, and Guess will turn the screen. Well, I mean, Guess will turn it so you can see the screen, okay? All right, so Lauren, what you're gonna do is you're gonna hit that button right there, the one that has the triangle. Yeah, the one that's like a half crescent moony thing on a sideways. Okay, so you're just gonna hit that button. Okay, and hit the button again. Oh, okay, so hit the button again. Okay, it stopped by itself. Okay, so sit down for a sec. Guess we're gonna turn it so you can see the screen. Okay, it might be a little hard. And what I'm gonna do is I'm gonna change the scale. And I don't care so much about the position versus time graph, but I care about the velocity versus time graph, and I want that to go from 0 to -2. So I want that to be 0. Oh, shoot. That totally did not do what I wanted it to do. Hang on. Graph options. So that can go from 1.2. Zero. Graph 2. That's what I want. Okay. So there we go. All right. Guess, can you see the graph? It's kind of blurry.
Oh, no.
Okay. So first of all, let's go up a little bit. Okay, so I understand that it's blurry, and I am sorry that it is blurry, but what we're gonna do is, who's got their phone and whose phone is on? Okay, so, did everybody have their phone? Okay, so what we're gonna do is, Sophie, you're gonna take a picture of this, and you are going to put it into the collaborate, not everybody, okay? Because you're gonna take different, like everybody's gonna do one, okay? So Sophie, take a picture of that, pop it into the collaboration space under ramp demo, okay? And then what do you think is gonna happen if I add a book? Okay, so Eva says it's gonna go faster. How are we gonna see that on the graph if it goes faster? What's gonna go down more? The slope of what? Which graph? This is the distance graph. This is the position, or this is the distance or the displacement graph. This is the velocity graph. The one on the bottom is velocity. Be bigger? More negative? Okay, so Fiona says the graph of the slope of the velocity graph will be more negative. Lauren, I cleaned that. Could you do that again for me? Okay, so, yep, hit the button. Maybe, okay, it stopped by itself. Okay, so I got to change the scales back. So give me a sec here. Graph options. This, go away. Okay, so we got a bunch of junk on the end, but somebody else, Eva, take a picture of this. Okay, focusing on this part and stick it in. Okay. So what's going to happen if I put 3 books under there? What's going to happen? It's going to go faster. Okay. So how do we measure acceleration? Or what is acceleration, Annabelle? It's a change in velocity over a change in time. Okay. So if I start with a velocity of 0 up here, and then it has a bigger velocity when it gets to the bottom, my object is what? It's accelerating, okay? And if it has a bigger velocity at the bottom, what can you say about its acceleration? It's got a bigger acceleration, okay? Guess agrees with us, yes? Okay, so what do we, if I'm raising up here, am I gonna have a bigger or a smaller velocity at the bottom if I have more books? A bigger velocity at the bottom, so my acceleration should be bigger. Okay, Lauren. Okay, that works. Thank you. All right. Let me get these back. Maybe we'll only do 3 books. We might not need all of them. Okay, so somebody else take a picture of that one. Okay, Annabelle. You can stand up. As long as it's less than 10 minutes that you are in somebody else's space, we're okay with the mask. Okay. Get a different one of these. All right, so let's just go right to 5. We'll skip 4. Sorry. All right, really high now. All right, Lauren, if you please. Yeah, you should have seen it when I was doing it by myself. You may have heard me if you were in the art room, because everything fell on the floor. Everything, I started with 5, and everything just like this, and it was awful. It was just one of those, oh my goodness. I should have known that was going to happen. I'm surprised Ms. Cass didn't send somebody in to find out what had happened to me. Okay, so one more picture here. Keeping in mind we're focusing on this part here. Who's going to do it? Somebody's got to do it. Yeah, that's because I was moving. In an ideal world, I would have had one of you catch it from, but it's like I can't. It was, you know, as it is, I've put Lauren at great risk. But because you probably would have gotten in the way of the motion sensor. Okay, you got the picture? All right, so let's go back to here. Guess I'm going to move you again. Don't get vertigo or anything. Yes, dear. I don't know what to tell you. Hopefully we'll have enough so that we can see what I want to see, because then my power's going to die too. It's going to be fantabulous. All right, so collaboration space. Anybody got pictures in there in ramp demo? Or did you? Oh, there we go. Okay, so let me share my screen again. I need to go back to here, share my screen so guests can see what I'm talking about, and we can look at all of these at once. Okay, so we can even do that. So what we really want to be looking at here is acceleration, okay? And acceleration is, like Annabelle told us, the change in velocity over the change in time. So even if we just look at these graphs, so here's the first graph, and you can see where the final velocity is. Okay. And we'll make this one bigger too. And we can see where the final velocity is. Okay. As we add more and more books, they'll come. As we add more and more books, what's happening to the final velocity? Dagny. Well, don't worry about the this way. Worry about what its value is. It's what? Well, the final velocity can't really get.
Like the line on the graph representing the velocity.
But I'm asking you about the final velocity. What do you know about the final velocity? The value that I circled. On the graphs.